So this says clearly why the Renaissance and Baroque choral music, when they were using the church modes, they were using the modes, that music is more effective for that very reason, is because they have a wider range of tonality. They have what I wrote here. Well, they have wide gradients of what a G is. A G can be 5 different kinds of G.
Right.
And so you have a wider variation, and in consequence to the variation of the tone, you have a wider overtones, and when they lock up, you can get that spike to infinity that you're talking
right.
about. And they lock up for that reason. That kind of spike you can't even get in equal tempered scales because people aren't adjusting that way. So the choral music of the Baroque and the Renaissance, when they were using the modes, they had a specific reason for it, because it was more effective musically and it made more sense.
Well, it gives you more of a selection too.
Yeah. So it wasn't like they were primitive. They got a lot more variety than we get out of the equal tempered scales. So I think with a musical sample for your lecture, I might just simply produce one of these scales, because I can create with an oscillator.
That's what I'm after. So you can hear what they sound like.
Exactly.
Yeah.
So with an oscillator, I can create these precise frequencies and play the Dorian scale in tune with itself, and then play a equal tempered scale to show how different it is.
Right.
And you'll be able to hear the difference. So that'd be one good example for the lecture. And as far as questions for you, I did want to ask. So the musical pitch ratios in the Pythagorean scale, do those same ratios relate to the properties of electricity, like they relate to the?
No,
they don't.
Well, there's not. It's a number system,
right?
That you could build an electrical system around,
but they don't directly relate.
It's not something that you need in electrical engineering.
Oh, okay. They don't really apply to electricity, those ratios.
Unless you're working with harmonics.
Okay.
In power systems, if you're working with harmonics, well, then there is a relationship there.
So in power systems...
But that's not normally done.
Yeah. What is the purpose of harmonics within a power system?
They're parasitic.
Oh.
You don't want them.
You don't want them. You want to get rid of them.
Yeah, you want to suppress them, or give them an opportunity to build up any intensity. That's the problem with the 3-wire or 4-wire 3-phase, is now you have 2 frequency modes, 60 cycles and 180.
Okay.
So now you have 2 frequencies in the power system. One is parasitic. So you have 2 power flows in the power system. One contributes to the flow of energy. The other one just gets in the way and distorts the waveform.
Okay.
But that's not, the electrical engineers don't figure that way.
Yeah.
They just tend to ignore it.
What does it do to the power systems?
It causes it to heat up, make interference with other power systems.
Make things blow up. Or not?
Well, it can.
Yeah, sure can.
Substation blowing up in Fallon because of Walmart.
There you go.
Yeah, they tried to hook up a China Mart, and the Harmonics burned out the substation transformers.
Wow.
Because the engineers don't know how to block the harmonics, and the contractors that put the wiring in the building will always do it the wrong way, because everybody does it the wrong way. They'll do it the wrong way because the lemmings all park in the same direction.
That's the way it works.
Right.
I have a question for you that's borders science and metaphysics. I mean, I don't know how else you can do it, but just let me ask you, from what you know, do you feel electricity comes out of the ether, like in electrostatic or magnetic, through electrostatic or magnetic forces? Is that where it comes from?
Well, electricity is ether polarized into those things.
Polarized into those things. So
ether's not there until you want it to do something. That's why it can't be. That's why they've never been able to identify it. It's like a genie.
Okay.
It's dormant. It's not there. It will not manifest itself.
Does it take human will and action to make it, or can something natural make it?
Nature seems to make quite a bit of it.
Okay.
Considering the sun's charged to 20 billion volts.
There you go.
And the ionosphere, you know, it's probably got over 1.5 million volts on it right now, and we're standing in 600 volts of it.
So what happens in an electrical storm?
Then that all gets turned up.
Crank it up. There you go.
Right.
So is music coming out of ether too? Would you guess?
Well, the atmosphere is the ether.
Okay.
So it's like if there's no wind, you don't really know the air's there, kind of thing. You can,
Yeah.
atmosphere is analogous to the ether.
Okay.
But then the question is, does music influence the ether,
Yeah.
like electricity?
Right.
So that's kind of what the presentation, you know, that's the end result.
Of this presentation
Well,
is that?
not the end, you know, the whole focus, but that's the question: is how did these people make rocks float in the air, or you know, the walls of Jericho fall down, or whatever? What's the
Well, that's what
engineering
we're talking.
basis for it?
That's what we're talking
Yeah.
about when we're talking about harmonics, like the harmonics of three voices locking in and creating that spike to infinity.
Right.
Because if you have three monks at specific pitches, absolutely in tune to each other.
Well, with only 3 harmonics, you know, it won't. You're not going to get the
Well,
biggest surge in the world, but nevertheless, it's going to be, you know, quite peaked up.
Yeah, yeah.
And then there could be something beyond going on.
Well, I think
You know, if the ether is influenced by sound as well as the atmosphere,
right.
then, you know, that takes it to another level.
And the sounds could be multiplied depending on what space the monks are standing in.
Well, the space that you're making the music in is just as important as all the rest of it.
Exactly.
Yeah.
Yeah. That's why choral music can be effective in a smaller space or a larger space, and the best choirs will tune themselves according to the space they're sitting in.
Yeah.
Literally tune the pitches of their voices to suit the space. And
Yeah, well, then the wavelengths all fit inside of it right. And
That's
then you
right.
get the right patterns, the
Yeah.
geometric patterns that you can't see with your eye.
And
They're
my
extremely
sense,
complicated.
It
I mean,
is.
if you could make them appear, it would be mind-blowing.
yeah, and this is where the
So I can feel that stuff in these organ concerts flowing through my body.
yeah,
It's like those little, science book diagrams of atoms, you know, with little balls with straws stuck, you know, and it makes that kind of lattice.
yeah,
I can feel these things moving through my body, wavering around.
yeah, yeah,
So they're there in the space. That's what the music television gives a portrayal of that.
right,
It's the music and the space. It's the space that actually makes a lot of the pattern.
right,
So a different building will make a different pattern on the scope, even though the music would be identical.
right.
So that's what you're saying, that these people are going to lock their voices into whatever mode that
Lock.
the space naturally wants to operate on, and it's overtones.
Right.
Because the space itself is a musical instrument.
Sure. And
That's what these cathedrals, the way they're built, is perfect for that. It's like Alexanderson himself designed them.
Yeah, yeah. Because the original the architects back then knew instinctively. They might not have even had the math for it. But
Yeah.
They knew how to make the sounds bounce around within that room.
Yeah, well, how did Silberman make a 10,500 pipe organ with a mechanical connection to each pipe? Could anybody do that today? Plus, he had to analyze the waveforms of the church before he built the organ in proportion to it.
Right.
You know how he did it?
No.
It's the impulse method. He walked in the middle of the building and took his cane and threw it on the floor, and then listened to the sound of the building from the echoes and the sound moving around, and then analyze that in his head, and then he built his organ out of that. And back then there was no insurance.
Yeah.
You got your head cut off.
It was really clear. Yeah. It was the same with musicians. So the composers in the Renaissance and Baroque both did the same thing. They judged things by their ears.
Right.
What sounded right to their ears was the linking up of overtones, and so
Right.
they wrote music appropriately for a small space or a large space, depending on where the king was sitting that day.
Yeah.
And that's why the music resonates so well, because those overtones are locking up, and they were
Right.
using scales appropriate to that. So that's what we're talking about when we're talking about this power of sound, turning it into an energy that can move a rock. It's the linking up of the long series of overtones. So if you have a group of 12 monks or 20 monks sitting around, each given a tone and specifically cycles per second. Each monk has a different cycle per second, and they lock up, spike
Well, it's
to
also the
spike to infinity,
the
and
phase
and
displacement, too.
phase displacement.
Yeah.
And they spike that to infinity and not hold it for a second, but hold it for like 5 seconds.
Well, it seems to be a launch, but at any rate, according to the person that wrote that one book, the situation is not energy-based. Whatever was going on with the Egyptians and all that's not energy-based.
Okay.
So it's not the collective energy of the harmonics, it's the fact that the music is doing something to the ether.
It's
Or it has an
affecting
influence on matter.
On matter,
There's a
and
direct influence on matter that is not based on energy.
excellent. Yeah, that's a really
Now,
important.
the Tibetan, rock launching appears that it could possibly be energetic. The light bulb jumping, off the desk,
Right.
that could be attributed to energy. It was a 200-watt amplifier cranked up all the way.
Right. The spike that you saw, was it on an oscilloscope that you saw the quick spikes to infinity?
Well, that's just standard engineering knowledge.
Okay.
So that's a real severe complication, like in long-distance telephone,
Okay.
particularly for broadcast music and stuff, to carry FM station signals or TV pictures.
Right.
So if there's the thing is in a perfect transmission line, if you have a synthesizer or a piano or whatever, and you put your arm down, you play all the keys simultaneously. They all come on at once and go off at once.
Right.
At the other end, they all go off and they all come on at once. But with these distortions of propagation, because of imbalances and stuff, what normally happens in a real system is you can play them all simultaneously, but at the other end, it'll start with the top one and it'll go down the scale.
Oh.
And you don't want that. So if you have a situation like that, then all the harmonics that made a rectangular wave that has a reasonable amplitude that's not going to overload your amplifiers, right? You keep it within like 30% max or whatever, and you're safe.
Yeah.
Well, if those harmonics get all twisted because they're getting there late, or early with respect to each other, then at the next repeater station, those harmonics might be in such a way that now you're getting a voltage peaks, like I showed you on the diagram of maybe 8 times the line voltage. The amplifiers will clip and the whole signal will just be trashed.
Right. So that's a normal phenomenon then.
Yeah, it's equalizing and loading. The loading networks take that out. So the whole problem with electromagnetic wireline transmission is the magnetism disappears by losses faster than the dielectricity. So if you charge the line up with magnetism, it goes away within milliseconds. But if you charge the line up with dielectricity, it'll stay charged for several seconds.
Right.
So that just twists the whole propagation. So all the frequencies now propagate at different rates. And your phases all change.
So the current electricians that work on our utility...
well, the power companies don't have to take
grids,
that into consideration because they just operate on one frequency.
Sure.
But not when it comes to a telephone and particularly music and well, now everything's digital, so.
Right.
So it's not real anymore.
Do the engineers working on our power grids know anything about dielectricity?
They don't know anything about anything.
There it is.
Yeah. They're software jockeys.
Yeah.
They don't know how to do anything. They rely on computer programs like the San Onofre nuclear power plant.
Right.
They relied on computer programs to build the new boilers for the thing, so they failed in 1 year.
Right.
$10 billion screw up.
Yeah. Because digital reality is not reality, it's a virtual reality.
Right, it's non-reality.
It's non-reality. And so stuff will blow up.
Well, you don't know what it's going to do.
You don't know what it's going to do.
If it doesn't represent what's happening.
Yeah. So in measuring...
harmonics right now are the biggest problem in the power system.
Uh-huh.
So the big screw-ups now in the grid are harmonics and susceptibility to EMP. Those are the two things that these people don't really know a lot about. And they can't even do basic stuff like figure out where to put the guy wires or maybe put a pole in straight.
Right.
You can't do anything anymore at all. It's just the whole
So
thing.
what would guard a power grid against EMP?
Well, you got to have suppressors, and you have to have transformer banks that block that stuff from progressing through the grid. So that's not...
Stop it, yeah.
Yeah, to block it off, at each substation or distribution station, and you have to have... They have nonlinear resistors now, that they use for lightning arresters and stuff, and you have to place those things at regular intervals down the line.
Right. None of that's in place right now then.
No, it's just that the terminal terminals at the station, there's no sequential, arresters like line loading going down to prevent this traveling wave from building up.
Right.
So you don't want it to be a big head to come building up, with a long tail and have to cut and absorb the whole thing at the substation. You want to, prevent it from building up by burning it off on the way down.
Right.
So it's not expensive or hard, and you have to have transformers where there's no metallic connection between the sections that it can propagate.
Yeah.
But they're doing the opposite. So apparently, from what I understand now, the basic impulse level ratings for all these substation transformers has to be higher now than it was before. Because the way it's connected, the impulses, the transients, the things that cause all the problems on the line are now higher voltage than they used to be because of this type of configuration.
Right.
So they have seminars and this stuff, and they all scratch their heads in stupidity, and the whole thing is laughable.
They don't know what to tell each other.
They have no.
It's
like the situation with China Mart. Okay, they build a big China Mart. They have all this gaseous discharge lighting, so you have to use 480 volts because the amount of power required. So instead of hooking the lights up in delta, they hook them up in Y with a fourth wire, which costs a lot of extra money. It's a bigger pipe, another cable, all that stuff, and then they make the lights 277 volts. So it seems like the voltage is lower, but in a 480 system, it's always 277 volts to ground, whether it's Y or delta. So by hooking the load up Y, is now all the harmonics, which the lights generate, lots of harmonics, and the ballast cores and all that type of stuff, is it generates 180 cycles a second. So in three-phase, three-wire, the 180 cycles a second is shorted out in the windings of the delta-connected transformer. They can't go anywhere. But in a four-wire system, is the three-phase 180 cycles, it can't be three-phase, it's single-phase. So now, instead of having a ballast system where you have no neutral current, now you have full neutral current, but at a different frequency. So then you go, if you want to go that route, then when you get to the supply transformer that runs the shopping center or whatever, then you take that Y connection that you're supplying to the shopping center, and you hook the primaries in your transformer in delta, and then the harmonics get locked in that loop, and they won't find their way back in the power line. You stop it at that point. But what it is those windings are going to get hot with all that zero sequence current. So the proper thing to do is to connect, like the Navy does, is to connect all the light fixtures 480 in delta.
Right.
And then none of these things exist.
Yeah.
There is no heating in the transformers.
You're saying
no
what you're
harmonics,
describing
it's
is
cheaper.
Yeah.
On top of it.
What you're saying is standard procedure for building shopping centers. Or
Yeah, standard procedure is wrong.
Yeah, it is.
Right.
But it's cheap, and that's why they're doing it.
Well, it isn't.
It isn't cheap.
No, it's not cheap because you have to have one size bigger pipe, and you have to have another copper cable.
Okay.
And the losses go up.
So they're just not thinking.
No, because everyone does it that way. So I had, electrical engineer, this guy Chris Carson, and I'm visiting him. He's, the chief electrical engineer for facilities management at UC Santa Barbara. So I see him out in the field, and he's supervising the installation of a football field lighting system with, 480 volt. So instead of getting 480 volt ballasts, he gets 277 and has them put the whole thing in 4-wire. And I go, why did you bother putting the thing in 4-wire, Chris? There's no reason for that here. There's no, line to ground type switching with just one pole or whatever. It's all just main switch. And no, that's just,
Just the way I do it.
It's just, he knows better.
Yeah, he knows better.
But he did it anyway. And he can't explain why he did it anyway.
Yeah.
He gets irritated by it. So what are you going to do at that point? It's a mental pathology.
It is.
Humans are compelled to do the wrong thing.
The wrong thing.
It's historically given
for no reason at all.
No reason at all.
I think Robert had some questions for you. You want to come talk, Robert?
Okay.
For no reason at all.
What can people do at home to benefit from the philosophy of music?
Listen to it.
Listen, okay.
Listen to it.
I wanted to think about these, yeah.
Turn off your maggot pod and your silly phone and listen to the music.
Okay.
Preferably live.
Yeah.
How should we be measuring music and its effects?
Well, I don't know. You're kind of asking questions that are out of my
Well, you mentioned it, for example.
Well, if the crowd gets up, and starts beating each other to death with baseball bats, that would be one,
One measurement?
that would be one measurement.
Okay, but you also talked about the guy who used to throw his cane in the cathedral, little
Silberman.
Tricks, yeah, little tricks like that. Is there any other tricks you can think of? Analog techniques, like for a musician who wants to improve upon his skills?
I mean, you're really going out of my area. So,
Okay.
Yeah. If you want to improve on your skills, then practice more.
Okay. Okay.
That's the only way to do it. The more you play the instrument, the more you've improved your skills.
What would you say about what are the problems of modern day measurement, those techniques used by academia?
Oh, you mean like the system of units and all that?
Yeah.
Oh, they're all screwed up.
Okay.
Yeah, they're all screwed up. The dimensions don't work out. Things that have no mass involved have the dimension of mass attached to them. Everything's multiplied by 1 over the velocity of light squared. And then for the fun of it, you either multiply or divide it by 4 pi. And then sometimes you have to divide it by 10, but other times you have to multiply it by 10 billion. And then, but sometimes the speed of light's not squared. And then might all be per units centimeter, and then it'll all be wrong, and none of it fits together, and you can't make any sense out of any of it at all.
Okay.
Yeah.
So
wrong.
Does everyone assume the speed of light is constant? They still assume that or not?
Well, that's that's a given in that world. The speed of light is constant.
In their world, yeah.
2.998 times 10 to the 8th meters per second.
Yeah.
But why does it have to be constant? And considering that your measuring instruments all operate on something that's influenced by the speed of light, you can't measure change in the speed of light because everything's changing with the speed of light. That's what that monochord thing, Flood, he's got the little hand coming out of the clouds. It's turning the tuning key.
He comes out of the ether.
Right.
Tunes it up.
It changes frequency.
That's a beautiful illustration for that reason, because the hand is coming out of the ether to tune the instrument.
Right.
Yeah.
So the frequency can't be the same.
Okay.
But at any rate, you take it as unit value because it seems to be the same or whatever. So that's not the complication, because the speed of light shouldn't even be in the equation to begin with.
They shouldn't be using it as a constant because they can't.
Well, it shouldn't be. Electrostatic units should not have speed of light in them.
Okay.
It screws everything up. That's when you're in electromagnetic units. So you end up with an extra time squared and an extra centimeters squared. But going between the units, you have to use the speed of light. But then the thing is, that's because of the way they approach it. If you don't keep dividing everything up into these little unit squares and unit cubes and unit lengths, then it's time. There is no velocity. It comes out to be time. And that could be any value depending upon the proportionality. So the speed of light at that point is not necessary anymore. Enter into the formula. And there's no reason to have mass involved in geometrical dimensions and charge and all these other things. The physicists have managed to jam all this stuff into all the dimensions even though it has no place there. So if you have the inductance of a coil, that's strictly geometrical. So why should there be the dimensions of grams involved? It doesn't matter if it's made out of aluminum or copper. It's still going to give you the same inductance.
Right. So their measurements
grams.
are...
The coil might be a little 5 milliamp one, or it might be something that sits in a substation. It's geometrical. It's proportion, like the musical intervals. It has nothing to do with mass. It has nothing to do with charge. It has nothing to do with the speed of light. So why are all those things piled onto it?
Yeah. So their measurements are messed up because they're adding a whole bunch of variables that don't even apply to the situation.
Yeah, so you can't analyze it.
You can't analyze it.
Yeah, and the practical measurements have all these constants and factors attached onto them that make them, they're no longer really truly connected to the thing that the measurement's all about. It's in some other dimension.
So does this...
And also, there might be two, a volt has two meanings, and so does an amp. Depends where you're at. It might be right in one realm, but if you try to use, one expression of volt in another realm, it doesn't work. Everything's all, and so they just lump the two together without distinction. So I gave in the last presentation that thing about how the velocity of light appeared, in the measurements originally. They were puzzled, Maxwell and all them, that in one system of measurements you get one value, but if you try to measure the quantity of electricity with another method of measurement, it gives you a value that's the speed of light off, even though there's no speed of light. That's what got everybody all, whipped up and created this relativity thing. It started with Maxwell.
Oh.
So there is no speed of light, but numerically and dimensionally it's there.
Oh.
So is it a speed or is it a relationship? It's a relationship.
Mm-hmm.
It's not a speed.
Right.
So none of this stuff is addressed. And at that time, it was thought about, but now it's just, no one even thinks of such a thing. No one even has a clue. You just sit down and peck your computer and get the wrong answer. Close the breaker and get the big blue flash.
So is any area of physics that you know of working with things that are accurate or not?
I'm not a physicist. All I know is keep your quarks out of my condensers.
That's a motto. That's a really good motto. Did you have another question, Robert?
Yeah. What are the problems of digital sound?
Distortion. It can't reproduce transients like the ones we were talking about.
Yeah.
They're incapable. Like
They
I was
can't-
telling with the telephone line, if the square waves get turned into spike waves, the amplifiers can't handle it, and they'll overload.
And the digital
And the
sound-
digital thing, the slew, if the slew rate, the rate of change exceeds the stepping rate, then the whole thing just glitches on itself.
Right.
It produces a quantizing distortion and a spurious signal. That's why the choral music sounds so horrible when it's digitally reproduced.
Right.
It just trashes it.
Because
Because anytime they start making those waveforms, it just splatters.
Yeah. And
It can't reproduce it.
digital reproduction doesn't create the overtones like a human voice can.
Yeah, for hump and slap music, it's fine, but not
But
for
the rest of the thing,
not for
yeah.
real music.
Not
It
for real
involves
music.
phases, and references and stuff. In fact, actually, probably hump and slap and barking and all the rest of that stuff is actual consequence of digital technology. Maybe that's the direction it's moving in.
Yeah.
Because the music is like that. It's very mechanical and fascist.
Mm-hmm.
It's not really musical.
Sure.
It's just lurching, kind of,
Lurching and angry.
Yeah. It's convulsive.
Convulsive.
Convulsive. That's
Much
the word
different
for
from
it.
Thomas Tallis. Your
Yeah.
coyote liked Thomas Tallis, of course.
Well, it wasn't Tallis, but it was one of his contemporaries. I couldn't find it. I got the complete
Okay.
Tallis, but I couldn't find that piece of music. So it might have been Palestrina or one of the other guys.
Yeah, yeah.
But at any rate, I liked it, and the coyote liked it too.
Good. Was there anything else, Robert?
Is there a spiritual aspect to electricity or music?
Yeah, but I can't define it right now.
Yeah.
But that's
You
how
don't
it came
talk-
about.
You don't talk much
Yeah.
about your spiritual view of things, and do you have one? Have you formulated one?
Well, I try to avoid those kind of things, but that's what all these books are about, so I have to
Yeah.
use that terminology.
Right.
So I'm not quite prepared for that now, but I
So
will
you-
be when the time comes.
Yeah.
Would you say we live in an electrical universe?
Well, that's definite.
That's definitely.
So, I mean, it's pretty well understood in 19th century that, all of this matter is really just an aggregation of electrical forces, and there is nothing solid. It's all electrical.
That was-
That was all well understood up until the Einsteiniism set in and said there is no electricity.
That was 1905.
Yeah,
Yeah.
Basically, Einstein and his followers, in their own way, said there is no electricity. And physicists suppress any activity of electrical. They don't want nothing to do with electricity. They have their little electron steel ball bearings and their little, material things, and that's it. That's as far as electricity goes. So physics has nothing to offer whatsoever to electrical engineering. Whatsoever. It's useless. Cannot be applied.
You're talking about J.J. Thomson's work?
Well, that's a different type of physicist, because he was an experimental physicist, and he wasn't so much a physicist as what they called an electrician. He was an electrical scientist, but they lumped that into physics. But Thomson's not a physicist in the sense that we understand today. They would call Faraday, they call Heaviside a physicist. Heaviside's not a physicist, he's a mathematician. Heaviside never built anything.
Well, J.J. Thomson's book, Matter and Electricity, would you recommend that as a reading for people out there to get a
Yeah,
good
it's the
understanding?
simplest way to understand his idea that that the ether has momentum and stores energy and can act like a material substance. And that material substance is actually matter and inertia and momentum are all electrical. They're not related to matter, and it's inside, it's outside the matter. Just like Tesla's theory of radioactivity comes from the outside. Thomson's theory of material inertia and momentum and all of those type of things, it's not inside the matter, it's in the electrical field that's attached itself to the matter. And if you make that electrical field go away, the matter has no inertia. You can start it or stop it instantly.
Okay, thank you.
By his theory. But it makes sense. It fits in with everything else.
Okay, didn't J.J. Thomson have a bunch of experiments anybody can do in his book? I remember reading.
That's Lee Bond.
Lee Bond.
Yeah. Lee Bond, he was going for the internal radioactivity, but he was able to produce one of what Newton and all those guys is alchemical mercury. And he shows the experiment there. You can do it yourself. Then it will make any chemist turn homicidal if you tell him that you've done such a thing.
When did Le Bon do this experiment?
Oh, like 1890 or something, or 1900 somewhere,
How do you spell his name?
L-E and then B-O-N. It's called the evolution of matter.
And what was this achemical mercury? What was
Alchemical.
Alchemy.
Alchemy. What would
It's
it
alchemy. That's why Newton, was playing with mercury all the time.
Right.
Well, I don't know. I forget the Newton book now, but it's some kind of mercury and some kind of strange solvent.
do? What would happen?
And it's a catalyst. So what you do is you immerse aluminum in it, which is aluminum is passive or only slightly reactive to a number of things, but you let that mercury act on it, and then you pull it out, and it looks like aluminum, and it's not necessarily amalgamized or anything, but all of a sudden it's explosively reactive. And it can be used as a fuel in combination with water to generate hydrogen. So normally you can take the non-alchemical aluminum and put it in the water and it won't do anything, but you can take the alchemical aluminum and put it in the water and it will explode. But it's still aluminum, and there's no way that a chemist can explain how that happened. None of the mercury is used up in the process.
Wow. Safe enough to do at home?
Well, I don't know. You got to watch out what ends up flying in your face.
Okay. Perform with caution, please.
Well, I have to make mention of that, because there's all these impossible things. So if we're going to get into figuring out how, and it's impossible to figure out how something works, in other words, how do we make rocks float in the air with music, well, then we have to talk about other impossible things so that we can enter the world of impossibility and realize that it exists. And if a physicist can't explain it, well, then that doesn't mean that it doesn't exist. It doesn't matter if the physicist can't explain the light bulb flying into the air off the bench. Did it? If they can't explain it, well, then you have to turn to somebody else because they don't know. If they can't explain the alchemical aluminum, well, then that's too bad. Then maybe they shouldn't talk about it and they should go away instead of saying they know everything about it. And then what makes the dowsing rods move when I'm out there looking for bad cable splices or old ground rods? What makes them move? They do. They move.
So describe that.
I can find the grounding terminals. I can find the bad sections in the cable. I can do all that kind of stuff with the dowsing rods. I can even find lost stuff. So what moves the dowsing rods? What acts on the matter to make the dowsing rods move? Am I supposed to believe that I'm turning them myself with my hands? So there's an example right there of some kind of influence on matter that doesn't involve force and energy. And the power of the music to make the light bulb jump in the air. Well, then, maybe these Tibetans had a better system and they could make rocks fly in the air. Somebody claims they saw it and they described the process. It seems to be generally understood that's what they do. So, is that because physics says it's impossible? So then at that point we'll be ready to get into the impossible.
Yeah.
Let's start doing that at the lecture.
I think so.
Okay, well, that's enough for me.
That's good.
Thank you, Eric.
We got
Appreciate
plenty.
it.
Yeah.
Boy, we got good material there. Thank you.
That's beautiful.
I'm glad we met. This is fun.
Yeah, well, I'm glad you're enjoying yourself.
Yeah, it's fun
So-
stuff. Gives me a lot to think about, and looking at the tables that you've described, it gives me all kinds of ideas about ways to compose music that I hadn't thought of before. So That's a plus too.
Well, that's kind of the end aim of the deal, to get into all these scales and frequencies, is to do something with them.
Right. And composing music for singers who can vary their pitch at will and aren't tied to equal temperament.
Yeah.
Singers, trombones, and string players.
Right. Non-digital instruments.
Non-digital instruments.
Yeah, actually, you know, the organ is one of the first digital devices.
Oh yeah, analog or digital.
No, it's digital because it's fixed frequency, and digit means fingers.
Oh, okay.
Right, it's digital.
Okay.
And so that's what creates the equal temperament complication.
Right.
Because it's not, you can't digitize the process because it cuts out the variations.